Okay, so polar coordinates, we learned from our last class that you have an XY plane and you want to plot points in the XY plane. And Cartesian coordinates are XY coordinates. Polar coordinates consist of finding from the origin a radius and then rotating it some angle. And based on that, you can locate a point in the XY plane. And so figure 1 here shows you, again, this is exactly what I'm saying. A polar coordinate has coordinates r and theta. Again, I like to basically, from the positive x-axis, rotate an angle theta, and then go out a distance radius r. And we talked last time about plotting some different polar coordinates. We talked about, in example 1 here, how you can plot points whose polar coordinates are given. And for each polar coordinate here, maybe I guess I can highlight it one at a time, maybe, each polar coordinate, you're given a radius and an angle theta. So like, for instance, the polar coordinate in A here, 1 and 5 pi over 4. Pi over 4 is 45 degrees. 5 times 40 degrees, 45 degrees is 225 degrees. And so here in figure 3, they draw the point that has polar coordinate 1, 5 pi over 4. So from the positive x-axis, they do an angle of 225 degrees, and then from the origin, move out a radius of 1. And that's how you get the polar coordinate. For like C here, and we had talked about these before, but I'm just reviewing it with you. For C, you have the polar coordinate 2, negative 2 pi over 3. So for there, in the third picture here in figure 3, pi over 3 is 60 degrees. Negative 2 pi over 3 would be negative 120 degrees. So you go clockwise 120 degrees and move out a radius 2. And that gets you the third picture. Now for D, you have a negative radius, negative 3. The polar coordinate is negative 3 and 3 pi over 4. So 3 times pi over 4, that's 3 times 45 degrees, which is 135 degrees. So you go from the positive x-axis in the fourth picture here, you go 135 degrees. But then from the origin, you don't move forward a distance of 3, you move backward a distance of 3. Okay, and that gets you that polar coordinate. Are there any questions on that? Okay. So with polar coordinates, of course, you have, just like in trigonometry, you know that the cosine of theta is x over r, and the sine of theta is y over r. And so you have your standard equations, x equals r cosine theta, and y equals r sine theta. And of course, along with that, you have that r squared is equal to x squared plus y squared, and the tangent of theta is equal to y over x. So with these equations, which you know from trigonometry are true, you can convert polar coordinates into Cartesian coordinates and Cartesian coordinates into polar coordinates. Okay, so the book has some nice examples. Here in example 2, they say convert this polar coordinate, which has a radius of 2 and an angle of 60 degrees, convert that from polar to Cartesian coordinates. So, of course, you just apply the formulas, and you find out that x would equal 1 and y would equal √3. Okay, so you know, if you plotted that Cartesian coordinate 1 √3, it would land at the same point as the polar coordinate 2 pi over 3. Are there any questions on example 2? Okay, all right. Well, if we're feeling good, let's move on. Here in example 3, we want to represent the Cartesian coordinates, 1, -1, in terms of polar coordinates. So here they're giving you a Cartesian coordinate, and you have to write it as a polar coordinate. That means you need to find the radius and the angle theta. So of course the radius, that's easy to get. That's just the square root of x squared plus y squared, and that'll get you √2. The tangent of theta is y over x, which would be -1 over 1, and that's -1. And of course, the tangent of theta is -1 in the second and fourth quadrants. So which quadrant is correct? Well, if you look again at your Cartesian coordinate 1, -1, that Cartesian coordinate is in the second quadrant. Okay, I'm sorry, the fourth quadrant. That point lies in the fourth quadrant. And so the angle that we have to give has to be in the fourth quadrant. So you can choose either theta equals -π/4 or theta equals 7π/4. One or the other is fine. See, and you get two possible answers for the polar coordinates. And there are even more, right? There's an infinite number of answers, but polar coordinates are not unique. You can have a point represented by multiple polar coordinates. Okay, actually an infinite number of polar coordinates. And you know, are there any questions on that? So I'm just reviewing really example this appendix H with you. Let me just see how we're doing here. Hold on, let me see. I got to get my some reason my chat thing's not showing. Hold on. Man, I always one moment. Let me just say hi and see if it brings up the chat thing there. Okay, all right. All right, well, if there are no questions on that, let's proceed on. So what we want to do is we want to talk about graphing eventually a polar equation. Well, actually, that's now, right? And so, for instance, they say in example 4, what curve is represented by the polar equation r equals 2? Well, so what you're used to seeing is Cartesian equations. You're used to seeing all your equations have x's and y's in them. Okay, but now you have a polar equation. What curve is represented by the polar equation r equals 2? Well, the curve, all you're being told is that the radius r is equal to 2. Theta is allowed to take on any value you want. So here, the curve would have to consist of all points r theta, all polar coordinates where the radius equals 2. And that's just going to be equal in figure 6 to this red circle. Right? Because if the radius equals 2, analogy would be like if you had, like in Cartesian coordinates, y equals 2. If you had y equals 2, that would be a horizontal line, but it keeps going, right? All the y coordinates are 2, but x is allowed to vary, be anything you want. You get a horizontal line. Well, with the radius equal to 2, it's just a circle. Theta can be any angle, so that'll trace out a circle. in the plane. Okay, so that's an example. That's an example of a polar equation. Okay, are there any questions? Are there any questions so far? Who, if you're comfortable, maybe give a thumbs up if you're comfortable, at least reasonably. Okay. All right. Good. Good. A lot of Tina's a little bit unsure, but she might be comfortable. All right. Thank you, Michael, Marcella, Muhammad, Rodrigo, Candy, and Eric. Good. Good. All right. Well, then let's proceed on, because I'd like to try to give you a little class time for you to work on this the assignment for H.1. We're covering two sections in the appendix, H.1 and H.2, and I need to talk about H.2 also a little bit today. But let me at least let's try to finish up H.1 so that we can so I can give you a little class time to work. I get kind of the impression that how many of you is your time pretty now, like it's sort of like everything's kind of coming due and papers and things. How many have that feeling? Wow, it's a lot going on. All right, Mohammed knows what I'm talking about, and Tina, and so Michael and Kahindi, and so if I can give a little class time for you to work on your homework, Snega knows what I'm talking about. I think it'll be helpful. So, okay, let's continue on here. Here, in example 5, we want to sketch the polar curve theta equals 1. Theta equals 1. It's 1. There, you're not given any information on the radius. The radius could be any value, but all polar coordinates have to have an angle of 1. So theta equals 1 in radian mode is in the first quadrant, because if like theta were equal to 90 degrees, you'd be on the y-axis. If theta were equal to pi over 2, your angle would fall right on that vertical y-axis. Well, pi over 2 is greater than 1. If pi is 3.14, and 3.14 divided by 2 is 1.57. So theta equals 1 is definitely in the first quadrant. And what they've done is they've plotted 5 points here, each whose angle theta is 1, but the radius varies. 1, 2, and 3, -1, -2. And if you were to plot all possible points where theta equals 1, you would trace out a line. Okay, and so one thing you always have to ask yourself is if you have a figure, is it easier to represent the figure in Cartesian coordinates or polar coordinates? Okay, so like for instance, the circle where r equals 2. Okay, that's a circle with radius 2. What would the Cartesian equation be for a circle with radius 2? Can anyone chat out what the Cartesian equation would be? So in figure 6, we have a red circle where radius equals 2, centered at the origin. What would the equation of the circle be with like x and y? What would the corresponding equation be? Well, r equals 2 is the polar equation. Hold on, let me Let me bring up the whiteboard here. So let me see here. Am I able to? It's going to allow. Okay, that's not bad. That's pretty good. This is going to be the best circle you've ever seen in your life here that I'm going to draw. I'm going to try to draw it. Radius 2. Center of the origin. So the polar equation for this circle is r equals 2. The Cartesian equation for a circle of radius 2 centered at the origin would be x minus something squared plus y minus something squared equals something squared. So what's going to go here? What's going to go here? What numbers? What's going to go to the right? Oh, well, it's centered at the origin. So what goes here? To the right, you're going to have 4. I'm trying to, let's see, Kahindi. So I'm getting some different answers. That's right, Alan. And all answers are welcome. But the equation of a circle with radius 2 centered at the origin would be x squared plus y squared equals 4. I bet, you know, I mean, how many's it been a little while since they've seen that? Hopefully not too long. Okay, so Michael's seen it, and I mean, you know, you've all seen it, right? You've all seen it. But this here, r equals 2, this is a polar equation. It's a polar equation because it has a radius in it and it has a theta in it, although this one doesn't have a theta in it, but you know what I mean. That's a polar equation, r equals 2, and then x squared plus y squared is your Cartesian equation. Now for circles, which is easier to work with? Which is easier? Cartesian equation or a polar equation? Which is more simple? That's right, Kahindi. That's right, Colomb. The polar equation. So, I mean, you know, what can be more simple than r equals 2, right? So polar equations are very good when you're working with circular figures involving cosines and sines and radiuses and just circular things are very good for polar equations. Polar equations can represent graphs of certain figures very well, and where the Cartesian equations do not. Now, Cartesian equation is very good for like a line, okay? But so up to now, all your lives, you've been working with Cartesian equations. But now you're learning about some polar equations because they're going to come in handy for certain situations that we need to deal with. They even make, actually, they used to make like graph paper. You haven't seen like the quadrilled graph paper with the rectangles in it. How many have seen that kind of, maybe in the CVS or in the store? Sure. Well, they also make polar graph paper too. And polar graph paper, thank you. Polar graph paper consists of concentric circles. Okay, but since we have Desmos, you won't need to worry about that. All right, well then let me go ahead and go back to the book here. Are there any questions on this? So in WebAssign, when it says, give me a Cartesian equation, it wants an equation that has x and y in it. When it says give a polar equation, it wants an equation that has r and theta in it. Okay, so that being said, let's go back to the book here. Find it here. So let's go ahead and look at a figure that's more interesting. In example 6, they want you to sketch the equation that with r equals 2 cosine theta. Sketch the curve, sorry, with this polar equation, r equals 2 cosine theta, and then find a Cartesian equation for the curve. So for this problem here, what they do is they make a table of values. So remember when you first learned to graph functions, a function in terms of Cartesian coordinates is y equals a function of x, right? Y equals x squared, y equals, the sine of x. Those are Cartesian equations. So a function y written as a function of x, when you first learned about functions, like you would say y equals x squared, you wanted to see what y equals x squared looks like. And what did you do? You picked some x values for that function, and you computed some y values and plotted the points, and that gave you an idea of what that parabola looked like. Well, and you learned it was a parabola, y equals x squared. Well, we can do a similar thing with Cartesian coordinates. Here you have r equals cosine of 2 theta, right? That's your see, can I get this one? I guess I can't highlight it, but you have r equals 2 times the cosine of theta, and you want to graph this polar curve, okay? And what you need to do, of course, is pick out some angles for theta. And you're going to you notice here the angles of theta in the table, they're all friendly angles that you know from your trigonometry days. So, for instance, when theta equals 0, r equals 2. That's because the cosine of theta the cosine of 0 is 1. 2 times 1 is 2. And so the polar coordinate is 2, 0, right on the x-axis. That's the starting point. And then let's look here. Next they pick in the table a value of theta, pi over 6, or 30 degrees. Well, the cosine of 30 degrees is equal to root 3 over 2. If you just draw a 30, 60, 90 triangle, you'll see that. So 2 times the root 3 over 2 is 2. No, 2 times root 3 over 2 is root 3. So in the second line in the table, when theta is 30 degrees, the radius is root 3. And so what they've done here in the figure to the right, this circular figure, is they did an angle of 30 degrees and then moved out a distance of √3. √3 is 1.732, so that's less than 2. So, you know, that's not going to be as far away from the origin as 2, 0 was. And then pi over 4, that's the third angle they picked. Pi over 4 is 45 degrees. Well, the cosine of 45 degrees is √2/2. So r is equal then to 2 times √2/2, and that's √2. So the next point they plot has polar coordinate √2 pi over 4. They move out an angle of 45 degrees from the x-axis. They go counterclockwise, 45-degree angle from the x-axis, and they move out √2. Are we good with the first 3 points here on this picture? Again, it's just like when you learn to graph functions of x. You would pick x values and find corresponding y values and plot the xy coordinates. That's what we're doing here for our polar curve r equals 2 cosine theta. We're picking theta values, finding the corresponding radius r values, and then plotting the polar coordinates. All right, and we can keep going with this process. We can keep going with the process. When theta is, for instance, 90 degrees. At 90 degrees, pi over 2, that's the fifth line. The cosine of 90 degrees is 0. 2 times 0 is 0. So you have a polar coordinate 0 pi over 2. So that's like 0 pi over 2 would be equivalent to looking up in 90-degree direction, and the radius is 0. So that puts you right at the origin. Now what they do is they go into higher angles. So 2 times pi over 3, that's the next angle. That's 2 times 60 degrees, 120 degrees. But the cosine of 120 degrees is equal to -1/2. 2 times -1/2 is -1. That's how they get that radius value for 2 pi over 3. So what you do is you look in the direction of 120 degrees. You look in that direction, but you walk backwards a radius of -1, and that gets you at that point polar coordinate -1, 2 pi over 3. Okay, similarly for 3 times pi over 4, that's 3 times 45 degrees, which is 135 degrees. So you look that direction, and you measure an angle of 135 degrees. You're looking in the direction then of the second quadrant, that middle dashed line there, but you move backwards -√2, because the cosine of 135 degrees is -√2/2, and the radius is 2 times -√2/2, which is -√2. And so that means you walk backwards. You look in the direction of 135 degrees, but walk backwards along that line segment, and that gets you at -√2, 3 pi over 4. And you can keep plotting points and keep doing this, and eventually you're going to end back at the polar coordinate 2, 0. And you've traced out a circle. You've traced out a circle. Okay. Are there any questions on that, on figure 8? All right, well, let me ask you, in the circle on figure 8, what does the center of the circle appear to be? What does the center of that circle in figure 8, that red circle, appear to be? That's right, Kahindi, it's 1, 0. So now they ask you in the problem, the polar equation r equals 2 cosine theta traces out a circle centered at Cartesian coordinate 1, 0 with radius 1. We ought to be able to find a Cartesian equation for that curve, right? We ought to be able to. And it's not hard to do, because if r equals 2 cosine theta, but you can replace cosine theta with x over r, because that's the definition of cosine theta. Cosine theta is x over r. And so you get r equals 2 times x over r, and then that would be equal to 2x equals r squared. Okay, that's what it would be equal. If you multiply through by r, both sides, you'll get 2x equals r squared, which is x squared plus y squared. But then that's x squared plus y squared minus 2x equals 0. Now that's not a form you're used to, but look, we can complete the square and write that as x minus, we can write, hold on, let me see. We can write x squared plus y squared minus 2x equals 0 as the quantity x minus 1 squared plus y squared equals 1. You just add 1 to both sides of the equation and complete the square. Okay, if you need to, maybe I'll show that to you real quick. Hold on, let me get the whiteboard here. Okay. You have x squared plus y squared minus 2x equals 0. And that's the same as x squared minus 2x plus y squared equals 0. And we can write this as x squared minus 2x plus a number, some number, plus y squared is y minus 0, quantity squared. We could write it that way. Now, if we're going to add a number to the left side, we have to add the same number to the right side. And you have to ask, what's going to make this equal to x minus something squared? You know, what number is going to do that? And it's going to be 1. It's going to be 1. Okay. So you're going to add 1 here and 1 here. And then I want to be a little bit careful. Then you add 1 and 1, you add 1 to both sides, and then you're going to get x minus 1 squared, x minus 1 quantity squared, plus y minus 0 quantity squared equals 1, which could be thought of as 1 squared. So that is the Cartesian equation for a circle centered at 1, 0 with radius 1. Okay, so you know, I'm kind of giving you a guided tour here of this Appendix H. right? And are there any questions on that? All right, now, all right, then let me go back here. Go back to the book. So, all right, you learned here in example 6 of an approach to plot a polar curve by taking angles, finding radii that go with the angles, and then plotting the polar coordinates, just like you would plot a function in the xy plane. Okay, but see, now you know what a lot of functions look like. Well, there's a second way also to plot a curve, a polar curve, and they talk about that in this example 8 here. They want to plot the polar curve r equals cosine 2 theta, okay, in example 8. So what they do, and I think I'll work this out with you, they show the graph of r equals, well, I think this is probably, we can do this right here in the book. I think it's okay. So r equals cosine 2 theta. This is example 8 we're looking at. R equals cosine 2 theta is a cosine function with what period? What's the period of the cosine of 2 theta here in figure 12, for example 8? That's right, Candy, pi. You take the 2 pi is the normal period, and because you have a 2 theta, so if you had the cosine of theta, the normal period would be 2 pi. But when you have the cosine of 2 theta, well, the curve that goes through the angles twice as quickly, and so that cuts the period in half. 2 pi divided by 2 is pi. And they've graphed this cosine of 2 theta. The horizontal axis is theta, the vertical axis is radius, and they have 8 pieces of the curve there. You see how you have 1, 2, 3, 4, 5, 6, 7, 8. They've dissected this r equals cosine 2 theta, the sinusoidal graph. It's a cosine though, but it's, you know what I mean. They've taken the graph and analyzed it in 8 pieces. So let's look at the part. Let's think about the part that is from 0 to pi over 4, part 1. So let me ask you, from 0 to pi over 4, when theta equals 0, the radius is 1. But as the angle approaches pi over 4, or 45 degrees, does the radius increase or decrease? It decreases. That's right, Michael. The radius decreases. It goes from 1 to 0. Well, look at what they have down here then for the polar curve. They have a 1 here. So the 1, if we start at 0, theta equals 0, that part of the polar curve corresponding to 1 corresponds to our trig graph, because the radius starts out as 1, but it decreases to 0. Okay, so that gets you this is what's called a 4-leaf rose, and the first leaf, we get the top half of the leaf. Okay, let me know if you have any questions on that. Please let me know. All right, well then let's continue. Let's continue. Now our cosine of 2 theta, graphing it like a trig function, from theta from pi over 4 to pi over 2, that's your second portion of the graph. What's happening to the radius? I'm looking here at figure 12 now. When theta goes from 45 degrees to 90 degrees, is the radius increasing or decreasing? The radius is decreasing. That's right. Good, Hindi, because you're going from radius equals 0 when theta is 45 degrees down to a radius of -1 when theta is 90 degrees. Okay, so the radius is getting more negative. And if we go to our picture, then let's look at the 2 portion of the graph. The 2 portion of the graph is the bottom leaf left-hand side. So what you're doing is, if you look in the directions of 45 degrees and 90 degrees, if you look in that direction, but move backwards a negative radius, and the radius will get more and more negative as you go to 90 degrees, you're going to trace out that portion 2 of your graph. Now for the trig graph in figure 12, r equals cosine 2 theta, when theta is between 90 degrees and 135 degrees, the radius increases. It goes from -1 to 0. Well, that's going to correspond to the the bottom leaf right-hand side in figure 13. Because your angle, you're looking now in the direction of the second quadrant. Okay, like look at that theta equals 3 pi over 4. You're looking in the direction of 135 degrees, but the radius is 0. So you wind back up at the origin. And you can keep tracing. I mean, if like back when I was in taking this course, we had to graph our polar curves all by hand. There were no graphing calculators, no Desmos, nothing like that. So this is how we had to do it. And in a sense, technology is nice, but we can also lose a little bit of our ability to conceptually see things when we rely too much on technology. But are you okay, at least reasonably, with figure 12 and figure 13, what they're trying to demonstrate here? I mean, I know you have to practice a little bit. That's why I want to give you some time to practice. But are you at least reasonably okay with what they're doing? Okay, Michael's feeling good. Kahindi's feeling good. Okay. All right. Well, what I want to do, I want to go into Desmos, and this example 8, where we graphed the 4-leaf rows, r equals cosine 2 theta. Let me show you how to do that in Desmos. So if you go to Google, and you type Desmos, D-E-S-M-O-S, this is a tool that's used to produce graphs and other things too. But we're going to go to Desmos. So just type Google. Just go to Google, type Desmos. Actually, maybe I hate to bring. I mean, all you need to do is type Desmos in Google. I have, like, for some reason, my search window, I don't know. I don't always get the, like, the main site. I get these funny sites, and then my main site is like maybe the third or fourth choice, in Google. How many have had? Oh, Mohammed says that's ads. Ah, that's what's going on. There's stuff in ads like in the beginning, and then the good stuff comes later. Is that what's going on? Okay, yeah, it's definitely possible because I get this kind of, I'm able to work it. I'm able to work it out. But let me just. I'm sure there's a way to fix it. I just have to be a little more, comfortable with things. I think what happens is my Google was working perfectly, and then I installed something on my computer, and now I get this, instead of Google, I get Yahoo. And so, but I always had Google before, not Yahoo browser. You know what I'm talking about, I'm sure. So I have to figure out how to get rid of that Yahoo browser. Candy says, what is it called? A secure search? So you mean they're ruling out certain websites? Is that what you're saying, Kahindi? It's possible. Occasionally switches to Yahoo. Okay, well, I think, I'm sure you have a little more experience. You have to go to settings and switch back. So thank you, Kahindi. I will go to settings and I'll make a note of that and try to fix that. Settings in Google Chrome, I assume. Okay, well, look, how many have seen this before? Desmos. How many have gone to Desmos and seen this? Try it on your computer, see if you can get there. All right, Michael, Kahindi, Rodrigo has. How many is this maybe your first time using Desmos? Is anybody this the first time, or? All right, well, what I'm going to do, okay, Tina, it's your first time. Thank you for your honesty. All right, well, let me show you what I'm going to do here. I want to, and Felicity too. Okay, very good, very good. Thank you, Felicity, for your honesty. Well, we love our TI-8384 graphing calculators. We love them. Desmos is also another piece of technology that you can use to help you. So I'm in Desmos, and like if I type an equation, y equals x squared, okay, y equals x squared, hey, it graphs y equals x squared, and I can zoom out and zoom in, and there's a wrench up here where it has graph settings. I can adjust my axis, so that well, they have x is between -20 and 20, but I can have y to be between 0 and what. So the wrench, you can do a lot of things. And then there's a projector mode here. Okay, that just makes things a little bit more bold, I guess. That's fine. So what I want to do is I'm gonna use the standard window here that your TI calculator uses. So x-axis, I'll go from -10 to 10. And you try it too at home with your Desmos, step size of 1. And the y-axis is -10 to 10 with a step size of 1. Okay, so now what I'm going to do, I want to graph the polar equation. So this is a Cartesian equation, but I want to graph r equals cosine of 2 theta. So, hey, I'm just going to say R equals cosine of 2, and then theta, I'm going to type theta, T-H-E-T-A, and there's theta. Okay, and by default, it's letting theta be between 0 and 2 pi. All right, now clearly this window is, I really want a better window here, so let me zoom out. Oh no, zoom in, I should say. Okay. And there's your 4-leaf rose. Okay, so there's some really cool graphs that you can do. Really cool graphs. I'm going to do this one. Watch this. I'm going to do sine squared of 2.4 times theta. Whoops. I'm actually trying this for the first time, class. So let's see if it works. So it's kind of like WebAssign, I think, you know, how you type things in WebAssign. How about that, huh? Okay, so I'm going to do sine squared of 2.4 theta plus cosine squared of 2.4 theta. That's one of the that's figure 16 in appendix H.2. Let me see here. Hold on. Oh no, I want cosine to the 4th power. Sorry. It's complaining. Why is it complaining? Oh, look at that. Only the cosine squared and cosine to the negative first are supported. Okay, otherwise use parentheses. Okay, so what I got to do, all right, don't worry, class. I understand what they're saying. How about that, class? How many think that's kind of cool? I've graphed the polar curve R equals. Okay, Kahindi likes that. Thank you, Kahindi. Thank you, Felicity. Michael, so you see, it would be like a nightmare to use Cartesian coordinates, like, you know, y equals a function f of x. You'd have a piecewise function with like 100 parts in it if you had to graph that in using Cartesian coordinates, but polar coordinates are much nicer. Okay, so how many are liking polar coordinates? Okay, thank you, Candy. Yeah, you can really do cool stuff. Now in the book, by the way, yeah, okay. So let me do just one more. You've seen Desmos. Let me do one more problem with you, just because I want to do this problem because I know it's going to come up in your homework, the one that's due here on Thursday, H.1, and I want to do this problem with you because I know you're going to have probably questions on it. Okay, so let me give you a moment to copy this example down. The reason I'm doing this problem is I wanted to do a problem where you had Cartesian coordinates that weren't like nicely converted into polar coordinates. I wanted to do one problem like that. And then I think I'll be able to give you a little time to work. All right, so take a moment to copy the example down. Okay, so we want to find polar coordinates of the point that has Cartesian coordinates 1, -3. All right, so what would be helpful to do this problem? What's always helpful in trigonometry to have? Definitely a graph. That's right, Michael. So there are two parts to this. In A, we're going to get a polar coordinate where we restrict theta to be between 0 and 2 pi. We have to restrict theta because theta could be, theta could be, there are an infinite number of answers that theta could be, right? Because a 360-degree revolution gets you back at the same point. So in A, we're going to let r be greater than 0, theta is between 0 and 360 degrees. And B, we want the polar coordinate where the radius is less than 0, and theta is between 0 and 360 degrees. Okay, so let's go ahead and look here. So what I've done is I've plotted the point 1, -3. Here it is. And clearly the radius is √10. But I'll tell you what, let me talk about the picture a little bit, and then I'll let you copy it down, okay? Why don't we do it in that order? Because I think it'll help you then when you copy the picture. So for A, I needed a positive radius, and I got it. Radius is the square root of 10. But now I need the angle. Now I need an angle. So this is not like the angle here, this angle, is your reference angle. But it's not a nice angle. It's not like a 30 degrees or 60 degrees. You know, it's not pi over 6 or pi over 3 or pi over 4. The angle's going to be the arctangent of -3. That's what it's going to be, because here, since x is 1 and y is -3, the arctangent of -3 divided by 1, okay, I can, you know, add to that a little bit here. The arctangent of -3 over 1 is going to be what that angle is. Okay, one moment here. Okay, just ignore that. That's a telemarketer. So, of course, if we were to have our calculator in radian mode and type that in, the arctangent of -3, we would get some value. But WebAssign wants exact values, so we're not going to do that. But for part A, remember, WebAssign wanted an angle between 0 and 2 pi, between 0 degrees and 360 degrees. Is this angle here, is that red angle a negative angle or a positive angle? Is this angle here this angle's a negative angle. That's right, Cologne. That's right, Kahindi. It's a negative angle. And we want our angle to be positive. So how are we going to get a positive angle that lands, you know, right there? Well, you just take the arctangent of -3 and add 2 pi to it. Okay, and then that's gonna get you back at this spot. 2 pi plus the arctangent of -3 is the same as 2 pi minus the arctangent of 3, because the tangent function is an odd function, which means f of theta equals f of -theta. An odd function is when f of -theta. I want to be a little careful. I don't want to call it really theta because it'll get a little bit confusing. But, you know, an odd function is when you have f of -x, and that equals -f of x. F of -x equals -f of positive x. Okay, and the arctangent function is that way, acts that way. So we can write, I mean, this answer would be acceptable, but so would this answer. And that's what we have for A. Now for B, you want to have an angle that you want to have theta is between 0 degrees and 360 degrees, but the radius is negative. So what I do there is, okay, well, I have to find, I mean, the angle I'm going to need to use is this angle. I'm going to look in that direction. Well, that angle is just taking the arctangent of -3 and adding 180 degrees to it. That's going to get you, you know, right here. Okay, that's going to get you right there. I mean, think about taking this angle here the arctangent of -3, and adding 180 degrees to it, that's going to get you back here. So the angle is going to be pi plus the arctangent of -3, or pi minus the arctangent of +3. And then you move back a distance of √10, and that gets you right where you need to be at that point again. So this one's a little tricky. Let me give you a moment to copy it down and see if you have any questions. But everybody always has questions with this one, so I wanted to do this example. All right, let me give you a moment to copy it down. You know, a lot of times these problems, I mean, these kind of problems they're like so many of the problems in math. I mean, hopefully I've at least given you, helped you feel somewhat comfortable, but you're never 100% comfortable until you actually practice problems. And that's very important to do, you know. I notice, like, well, you know, it's just critical that you know, this latest material is going to be on your final exam. And we're going to talk about the final exam on Thursday's class, as well as we have to cover some new material on Thursday, but you'll have time in class to work on that material so that I can help you. But, you know, we're also on Thursday going to talk about the final exam. And this latest material is, you know, sections 8, 7, 8, 8, H.1, H.2. It's important for the final exam. So, you know, I want you to do well on the final. This is, by the way, this f of -x equals negative f of x. That's if you have an odd function. That's only for an odd function. Are there any questions at all? Okay, is anybody still copying the example, or are we good? Okay, Tina's good. Thank you, Tina. Thank you, Cologne. Thank you, Michael. Thank you, Rodrigo. All right, let me stop the recording.